Hi everyone, this is Nick Frashard with RadWave. Today I want to go over two different releases that were put out recently, 2.2.0, 2.3.0. So let's dig into it. So with release 2.2.0, for actual things that were improved, one was we had a really significant improvement in the download speed of for getting data from the Breakthrough Listen Open Data Archive. So I'll kind of demonstrate what exactly is happening there and how it was resolved. The second thing, these are all kind of small, but this one here is kind of low-level detail, kind of interesting, where there's a low-level time tracking bug that was causing the RadWave engine to fail midway through processing, just because of this discrepancy in a couple of numbers here. So we'll dig into that as well. And then for release 2.3.1, I added some new features into the natural audio processor within the RadWave Explorer. So we're now able to export the tags to a WebM video, so that way you can share what you are able to look at in this and have both audio and the video component to it. There's also now an ability to view the output of that in both like a full or just a visible portion of the spectrogram mode. So we'll see how that works. So let's get started with the RadWave engine. We'll see how things change there. So let's go back to the release known as 2.2.0 and start with the changes made in the RadWave engine. So for this top one, the download speed from the Open Data Archive, this here is the Open Data Archive, where the 2 petabytes of data that's hosted by the Breakthrough Listen team. So this is the format used to download that data. As you can see here, we're looking at data from GreenBank. We're specifically looking for the baseband data. That's what RadWave uses. This is the raw antenna measurements. And in this particular case, I'm looking for this target. You can see that we have all these different files that are available to download. You should be able to click on each one of these for some reason that's currently broken. But what we can do is just use a curl command. So if I type curl, if you were to try to download this file, just like normal, you can see that the current speed right now is extremely slow, and it's going to take about 5 hours to download this one file. So this is a 17 gigabyte file. It's just plain slow. But if we pause it, so if I just Control C out of there and I restart that same command, so what this is doing, this continue at, will make it pick up where it left off. All right, so right now you see that I have a file here. It's the one that we were downloading. It's downloaded this portion of it, which isn't the full set. So if I just restart it, we can see now that the download speed is orders of magnitude faster than it was before. And instead of it having 4 or 5 hours to download, it's now at 20 minutes. So I'm not sure why this is the case. I've just observed that that is consistently true. And when you try to download when you try to download the file in its entirety, you're throttled. If you try to download a portion of it that doesn't include the first few bits, the remainder of it downloads extremely quickly. And so using that that fact, I was able to change the process that the RadWave engine uses to download the files, where first it makes a request to download the first small portion of it, and then it picks up from there and continues. So this is just massively sped up the RadWave engine, which has been really helpful. So I'll demonstrate that here. So we're going to go to the same object. I'm going to go to one of the files that I have yet to download. I'm just going to do download only for right now. And you can see that now we're getting about 60 megabit per second. It's going to take about 20 some odd minutes to download it. And this used to be 4+ hours consistently. So yeah, and in prior versions of RadWave, downloading the file was the primary bottleneck to processing. The remaining stages still take non-trivial amounts of time, but this was definitely the long pole. It was definitely the thing that took the longest. So I'll stop this for the time being. All right. So the second actual feature fix that's non-negligible was this low-level time tracking bug. And so there's a paper that was released that describes the format of all of these files. And in the appendix B1 in that paper, there's a TBIN term and there's a CHAN BW term, so channel bandwidth and the time binning. So this is like the time resolution. Let's go to the paper just to see it for real. Yeah, so here in the paper we see that TBIN is a time resolution of incoming data. It's ideally equal to 1 over the absolute value of the channel bandwidth. And the channel bandwidth right here is the bandwidth in megahertz of a single channel. And this will be negative if the frequency axis is reversed. So, yeah, let's take a peek. What's really nice about this paper in particular is that it provides an example of what a typical raw header for break to listen data looks like. So I can take this directly. I can copy that. We're going to open up a Python terminal here. Let me just paste it. And I can do the same thing for the channel bandwidth. And I can paste that. And so it said that TBIN is equal to 1 over the absolute value of the channel bandwidth. That's in megahertz, so I have to multiply it by 1,000,000. And we see that TBIN is equal to 3.41333333 times 10 to the minus 7. And this here is also equal to 3.413333 times 10 to the minus 7. And these look as if, like when you just look at those values, those look the same. But if we compare these numbers exactly, we see that there's actually an extra 3 located in this term, and there's no extra 3 located in this term. And you might think, like, this is just a repeating 3. Of course, there's 3s that come after it. However, if you look at how the computer is actually representing this value, so if we look at the hexadecimal of how this is represented here, you can see that TBIN has a 0 in the least significant bits of the mantissa, whereas this value here has a 6. So these are actually how they're represented by the computer is actually different. And that difference, if you multiply these numbers by a large number, actually becomes significant. And specifically because these represent units of time and so in the RadWave engine processing, it's trying to keep very fine track of what the time is. And there's an enormous number of samples in these files and these collections. And when you multiply that time resolution by a very large number of samples, you actually get sample indexing errors if you were to use the tbin value versus the value derived from the channel bandwidth. So that's what I had been doing, was I was using these two terms interchangeably, even though they are not. So I had to really comb through the RadWave engine processing, avoiding the use of tbin, because this value here is exact. The channel bandwidth is exactly this value. This cannot be exactly represented by a computer due to this repeating 3. And then the other change I made, just to kind of hammer the point home, was to switch to integer sample-based time tracking everywhere possible. And then I only calculate the UTC sample times as required. So yeah, those are the two big changes there. So you should now be able to process, hopefully, any of the files that are available within RadWave, because RadWave restricts which files it's currently able to process. So if you have any issues processing any files, please let me know. You can just contact support@radwave.com. You can email me, so I can be aware of which files are still having some issues, because I can't download all 2 petabytes of data. So with the other fun features that were added into the RadWave Explorer, here, let's open that now. So this is one of the kind of interesting collections, this object DAG W75S off. I found at this particular frequency. And we'll use the one where audio is enabled. So for the time being, I'll disable the tag boxes. There's a little bug here where if you shrink the time, the power spectral density plot in the bottom is more interesting. And then I'll move this so we can kind of see what signals are in here a little bit better. So in this region of the spectrum, you have some interesting signals that pop up. So these, when I look at them, I see three channels of a communication type of signal. These are not, if you look at the full duration and time, these aren't slanted diagonally at all, like across frequency. So since they're all just at one constant frequency, it seems to be unchanging. To me, this just looks like a stationary, terrestrial, man-made interference type of comm signal that happens to be loud enough where the Green Bank Observatory is still able to hear it, even though Green Bank is pointed in a very different direction. But it looks cool, right? This has definite structure to it. This X pattern here is more than likely an acquisition sequence that the receiving radio can look for. It's something that's very, very easy to detect. And it can then, because it has this X pattern here, the receiving side can really narrow in and obtain the center frequency that's used for the data packets that come after this, right? Each of these packets that come later on look like data. And so let's say I want to tag this. I'll start with just a single one like that. And we can listen to it. See what does this sound like? Now, this isn't when we're listening to it here, we're listening to just a single sideband AM demodulation of this signal. But this signal is not a single-sided AM modulated data. So this isn't what the receiver actually hears. Yeah, so it's kind of fun. And then we can save this to a WebM file. So it'd be like a comm channel. That's what I think it is. So I can start this process. Okay, that's fine. So let's go to that directory. And here's my comm channel WebM file. And now this you can share on social media, wherever, a lot more easily than you can with other mechanisms. So the goal here is to be able to let people know what you actually found without having to share this entire data set, right? So this is just a lot easier to kind of get into the public, into the wild, without requiring people to download RadWave attached to your backend that where you hosted it, or reprocess the file themselves with the exact same parameters. So it's just a neat, simple way to do that. Yeah. So what else did I change? I can't remember. Oh, yep. So this full invisible playback mode. So when we do this here, there's two different modes, full and visible. So when we put visible here, this would only play just what's visible at this time. When it's in full mode, they'll go back to the and they'll play all that. So if you have visible active, here we can. So if you want to capture just like the squeaky part, right? I could get the duration to be a little bit smaller. I can bump this back up. Do visible. And then if I hit save to WebM, if it's just the acquisition part, that'll export pretty quickly. This is probably the shortest file I've ever created, so I'm curious if it'll actually work. Yeah, too small. It's always a bug. Let's make this a little bit longer. Yeah, 0.07 seconds isn't one frame of video, so it's gonna have a hard time with that. So now let's try it. Yeah, so you can show either just the visible portion or the full portion. So yeah, those are the main points I want to be able to highlight today. Appreciate you staying tuned, and let me know if there's any features that you're interested in seeing here. At this point, most of the bugs should be shaken out, minus some little things, but it should work overall. As you can see here, you can change the ID on what this is. You can write a little description about what you think each of these things are. So let's be like comms bursts, single channel. You can accept that selected tag, and then that tag is going to end up somewhere in here. Here we go. And then, yeah, so if you click on these other ones, it'll take you over to that portion of the band. All right. Thanks so much for your time today. Please like and subscribe and let me know what you think. Let me know if you do like things, don't like things. I love negative criticism. Positive reinforcement is great too, but when people tell me what's wrong, I can actually have a chance to actually fix it. So, yeah, you don't. I don't mind you being critical. Thank you. Bye.